Hello. So I'm Ivan. Yeah, we've done that already. So now I'm going to talk about another project, which is automatic retuning of floating point precision, which is done by me and William Moses from UIUC. So obviously choosing the right floating point precision is very important, because if you choose like too high precision and you didn't need it, you wasted a lot of compute resources, you wasted a lot of power. So there's been a lot of work with, especially with ML models, to try to get the precision as low as possible to improve performance, because we don't actually need like perfect precision there. But for example, if you go too low, you get like useless results. And in some scientific applications, applications like require more than 128 bits of floating point precision to work properly. And there's also work being done in that direction to improve precision. So there's a lot of important exploration work to be done with what we can do with precision. And also future hardware is getting shaped more and more by MLs, which require like lower precision, which is in contrast with what HPC and scientific computer requires. So existing approaches, I mean, to explore like the various possibilities that you have, you can like define macros and change your float type, or you can template your functions, or you can use you can change the floating point types to MPFR, which is a library which allows you to do arbitrary precision computation. But all of those have like some disadvantages, and I'd like to focus on one specific one, which is for example, ones that replace floating point numbers with some struct which will represent the floating point number, but the compiler doesn't understand it, then the program that executes will not reflect the optimized state, which is to say, for example, if you have a function which adds two numbers and then multiplies the result, or it was the opposite, I'm not sure. I hope it's the correct one. So that gets combined into an FMA if it gets optimized. But if you have like some opaque struct and you get your own runtime function calls to add and multiply, then you won't get this optimization. LLVM has no idea what's going on, and you just get the same code. So if you instrument your code, or like you have struct as your floating point type, and you try to do analysis on like the execution of the program, then you won't get the result that you would expect. So yeah, there's, for example, we tried FPBench, which contains like 745 functions with for floating point computation, and we run it with Clang 03 and FastMath versus 0, which is what you would get if you have opaque structs. And we find that like for 124 of them, we get mismatched results. So that's a problem if you want to like explore options with regards to precision. Yeah. So in our approach, we build it on the Enzyme infrastructure, which allows you to basically instrument all of your floating point computation. And that was historically done for derivatives, but now we use this for precision analysis. And this means that we can apply all of the optimizations that will be done before we instrument our code and replace our floating point computation. And we do this automatically. You can either call a function or like specify which function you want to truncate the values for, or you can specify on the command line to replace all of the floating point computation in the module. And we can do, for example, double to float, double to half, or if the platform supports it, or we can also insert runtime calls to the MPFR library so that you can do arbitrary precision, for example, exponent 5 and mantissa 20, or like whatever you want. And this is an example usage where we can call this function, which is like truncate this function for me, and you give it the function, and you give it what is the original precision and what precision you want it to truncate it to. And it will return actually a function which contains code for which the floating point operations are truncated. And you can also do that on the command line. You just say truncate everything from 64-bit floating point to floating points with 5 exponent of width 5 and Mantista of width 21. Well, future work, there's we expect a lot of fun analysis can be done with this tool, and it's all open source. Please go check it out and let us know if you have some interesting use cases for it. Thank you.